Good morning, Srini.
Good morning,
How
teacher.
are you?
Teacher, just give me 10 seconds. Hello?
Hi, ready to start?
Yes, teacher.
Okay. These are picture of various form of circular motion. And then the thing you need to remember is this is called rotation. This is called revolution. This example you can see in uh, like Disneyland. And then also you can also have aeroplane going in a circle. Okay, let us make a start. As far as syllabus concerned, if one angular displacement, angular velocity, express angular displacement in radian, define angular velocity and period, derive and use the formula. Then we go to centripetal acceleration, explain that uniform motion has an acceleration due to change in direction of velocity. Then we are supposed to derive this equation and this equation. Explain that under centripetal force, explain that uniform circular motion is due to action of resultant force that's always directed to the center of the circle. Use the formula, okay, and then solve. Solve problem involving uniform horizontal circular motion. Solve problem involving vertical motion or point mass. Knowledge of tangential acceleration is not required. It's not required. Let us make a start. Right? Remember the book next time to bring your book, your pencil, your paper, your calculator, everything must be ready. Angular displacement and angular velocity. Uniform circular motion. What does it mean? That a body is moving with circular path with constant speed. Right? The body or the object is moving in a circular path. Key is circular path or circle with constant speed. Right? The key is constant speed. Speed is a scalar, so it doesn't involve direction. No tangential acceleration. That means in this direction of the velocity, there is no tangential force or acceleration. That's the key to remember. You're not interested in tangential acceleration. Okay, so these are all example. And a roller coaster, motion of satellite, topic 6, and then car cornering. Okay. Linear motion and circular motion. Linear motion, we need the velocity. And then as in, right? Circular motion also, we need the same thing. Right? Instead of displacement, we define a new term. Instead of calling angle, it can go clockwise or anti-clockwise. We call it angular displacement. Then instead of velocity, since it's moving in a circular path, we call it angular velocity. The extra term angular, move in an angle in a circular path. Right? Newton's law tells us that when the path of the particle changes, the resultant force act on it. So from Newton's law, if the path of this one changes, it's supposed to go in the straight line. But instead of it going straight line, it moves in a circular path. So it means that there must be a force pulling it towards the center, a resultant force. And then Newton's second law, we'll be using all that. Right? F equals to ma, help us to find the centripetal force. If it has acceleration, it must have a resultant force called the centripetal force. So that's the direction of the acceleration or the direction of the force. Okay, so analogy, right? Time is the same. Whether it's a linear or circular motion, it's the same. But displacement, for circular motion, we use angular displacement. We call it theta. Right? It's a vector, remember. When it comes to displacement, it's a vector. Then velocity, we have angular velocity, omega. Right? It's a vector also. Acceleration, we also have angular acceleration, or we call it tangential acceleration. Relationship of circle, the arc length is radius times your angle. Same, velocity the same, r times omega. These are how they are related. We will derive this equation. And then acceleration the same, r times your alpha. Alpha is an angular acceleration, but we are not interested in acceleration. Force causes linear acceleration. So instead of force, when we come to angular acceleration, we need a torque. That means if we want to increase the angular velocity, you need a torque. Right? Force applied at a distance. So we are not interested in this one. This one is zero as far as we are concerned. Tangential acceleration is zero, not required. Okay. This is another part of physics. Okay, so some of the terms you need to know. Right? There is your radius. That is the center. To the particle from the center is the radius. That is the tangential velocity. Right? Tangential velocity, because it follows the direction of the tangent to the circle, or we call it velocity. And we got angular displacement. This angle theta, it has a direction anti-clockwise in this case. Angular displacement, not angle, angular displacement, and angular velocity. Right? The angle changes with time. That's the angular velocity. And we define the radian. What is meant by a radian? As long as that is the radius, that's the radius of circle, that is your r, the arc length is same as the radius of the circle, then we call this one radian. Right? It's the angle substance at the center of the circle, this angle, where the arc length, this is arc length, equals to the radius of the circle.
1 minute, teacher. Yes, Tata. Yeah. Sorry, teacher. What? Hello?
Okay?
Yeah, okay. Okay.
Right? Then we want to know the relationship between the parameters. Right? This one you need to remember from your maths. Right? Angle theta, radius r, can be small r, can be capital R, doesn't matter. And s is the arc length, the curve. Sorry, that distance. So you remember r theta. Show that one revolution is 2 pi radian. Right? One revolution is 2 pi r. That's circumference. Right? That's your s. And r theta. Right? Theta is s divided by r. So s is 2 pi r divided by r. So I've shown that cancel the r. So one revolution is 2 pi radian. Okay, I've just shown that, so we won't bother about that. And you need to remember about radian. One revolution is 360 degrees. Right? One revolution is 2 pi radian. 2 pi radian is 360 degrees. And then you want to find 1 radian, you just divide by 2 pi, 360 divided by 2 pi. Right? Remember this one, or pi equals 180 degrees. Right? 1 degree, you just divide by 360, this one, got that one. What is angular displacement? Same, then velocity. Except we define in terms of angle. Angle swept out by the radius. This is the radius. It turn that radius, that turn. an angle theta. So that's the angle swept out by the radius in a particular direction. That's important because it's a vector. Right side. Right? Unit, radian, angular velocity. Right? The angle is going to change with time. So we define another term, rate of change in angle swept out by radius in a particular direction. Right? So if uniform speed, then we have theta divided by t. But if it's changing, then you have to use calculus. D theta dt. When we come to rate, you have to use calculus. Right? It's a vector. So it's either clockwise or anti-clockwise. Unit, theta is in radian. Time is in second, so it's radian per second. Speed and angular speed. For a particular particle moving with constant speed v in a circle of radius r, how is the angular speed related to v and r? Right? That is the equation that we want. How to derive that? Right? Same. We let it be here. Initially, the particle is here with velocity, tangential velocity v. And then after a certain time, it will be here. Velocity changes direction, but the speed is still the same, magnitude is still the same. And then there's omega. So we have v equals to displacement divided by time. That displacement is the distance, not displacement, it's distance. That's the arc length. S divided by the time. Right? And that's the radius. That's the arc length there. So we replace the S with our r theta. Okay. S with our r theta. R is constant for the circle. Theta is the one changing, time t is the one changing. Well, okay, differentiate. Right? Differentiate this one. The same thing. Differentiate this one, you will get the same equation, but you get d theta dt. And then theta over t, we have defined it as your omega. Okay. And we get our relationship. V equals to r omega. Right? Stop me if I'm going too fast. What's the period of revolution? Right? Period is the time for the object to move one revolution, one circle, one complete circle. Frequency is the number of complete revolution per unit time. Right? It's either revolution per second or you can call it hertz. And the relationship is F equals to 1 over T. Right? This is not V, but it's a Greek alphabet called nu. Right? Relationship between T and omega. Right? T is the time for the object to complete one revolution. Right? One revolution is 2 pi radian. So we just use the definition of angular velocity. So one revolution, this is 2 pi. Then this become your period. Alright, that's the relationship. You can remember if you want to, if not derived from the basic definition, pi over t. Okay, what's the answer for this one?
This one, V equals to R omega.
Yeah, what's the answer? Well, this is taken from your book, page 106. If you have the book around, number 1. Okay, the minute hand will travel 1 round. 1 round is 1 hour. That's the time. We know the radius. So what's the answer? You want omega.
Boy.
Okay, the period for the minute hand is 1 hour or 3,600 seconds. So we got 2 pi divided by t. Right? This is a distraction. Don't need to use that unless you use velocity. 2 pi over t. And that's the answer. Boy, correct. Right? If you ask linear speed, then it's v times r omega. Right? There's omega. And there's your r. Calculate your linear speed. Okay, how about this one? A disc is rotating about an axis to its center and perpendicular to its plane. A point P on the disc is twice as far from the axis as point Q. Imagine what is happening. At a given instant, what is the value of linear velocity of P to linear velocity of Q? Okay, what's the answer?
A.
Right? We are just using V equals to R omega. Right? Omega is constant. Then you just take the ratio. Okay. For velocity of P, you are told that R is 2R, right? Twice. Right? Point P twice the radius of R of Q. So the radius of Q will be R. Omega is the same. Cancel. The answer is 2B. Wrong. Good try. How about this one? Which of the following statement is correct for a particle moving in a horizontal circle with constant velocity? Yep. What is the answer?
Oh, C.
Say again.
C.
Wrong. Remember, velocity is a vector. It has direction. So linear momentum follow velocity direction. It will change. Kinetic energy is speed. Speed changes, kinetic energy changes. Right? We are just using V equals to R omega. Omega is constant. V is constant in magnitude. Right? Magnitude only, remember. But it's a vector. It changes in direction. So kinetic energy is constant while linear momentum varies. It varies not in terms of magnitude, it varies in terms of direction. So answer is B. Okay. All right, how about this one? Showing you the picture. A point mass move through a circular arc of length L. That's the length L. And radius R in time T. What is the angular velocity about the center of the circle? Yep, what's the answer?
C.
Okay, let's see. Right, your theta is S over R. Use the symbol in this question. S is your L, R is still the same. So it's L over R. Use our definition for omega is theta over T. Theta, just place it there. So it's L over RT. Right? So answer is A. Sorry, wrong. A. Okay. Okay, let's carry on. Centripetal acceleration. We are just using Newton's first law. Same thing. This is your object or particle moving with initial velocity u. And it will continue with moving in a straight line. Right? If no resultant force x on a moving object, the object moves with constant speed in a straight line, or it means constant velocity. Right? It will be in a straight line, no external force, nothing. Right? Same thing from the first law, Newton's first law of motion. Throwing an object or a ball horizontally, what's happening? The resultant force acts perpendicular. Right? That's horizontal velocity. You throw the ball, the weight is pulling it down. That's the resultant force. So the resultant force will change the direction of the velocity or change the path. Direction of force is constant. In this case, always downwards. Always downwards. Never change in value. Never change in direction. So in this case, where there's a resultant force acting, the speed must increase. That's why we study in our topic 2, kinematics. That's the force acting. That's the weight. You move in a parabolic path. The force direction doesn't change. The velocity direction changes. Right? Both the horizontal speed doesn't change. Sorry, horizontal velocity doesn't change. Vertical now got vertical velocity. Right? Initially it's 0 here. Here the velocity changes because there's a force acting vertically downwards. So that's why the resultant velocity changes. Magnitude and direction. Okay, so the speed increases. So same in the circle, right? It's moving at a tangent to the circle. There's the center of the circle. There's a force acting. There must be a resultant force acting towards the center. So a uniform circular motion, the force is always perpendicular to velocity. On the particle or always towards the center. So we either say it's always perpendicular to velocity, or the force is always directed radially or towards the center, either along a radius or towards the center. The speed remains constant. Speed doesn't change. Force do not increase the speed, right? Because it's perpendicular to velocity. Okay, so particle instead of here, what's going to happen? The force pull it down into the circle here. Right? That's the resultant force, still perpendicular velocity. That is still tangential velocity. Right? Magnitude doesn't change, only direction changes. Right? So it's being pulled in again, right? Moving into a tangent. That's the purpose of this force. Always acting perpendicular to the velocity or towards the center. Okay, so we are just using these two laws, Newton's first law and Newton's second law, to calculate the centripetal force. Later on, we will see. Right? So this is just a review. Angular displacement, this linear displacement, this angular displacement. That's your velocity. That's your angular velocity. Right? It's moving a circular path. Object in uniform motion, accelerate. Right? When a body moves in circular path with constant speed, its velocity changes direction. Right? Remember, velocity is a vector quantity. So velocity changes direction means there's a change in velocity. Right? We will use all these steps later on when we derive acceleration. Right? So there's a change in velocity. That doesn't change. That is not zero. Speed is zero, but this is a vector quantity. So acceleration is the rate of change in velocity. That's how we define acceleration. not speed, right? Rate of change in velocity. So there's a change in velocity, there's a change in acceleration. The body accelerates, sorry. Change in velocity, the body accelerates. Magnitude and direction of acceleration, right, is always towards the center of the circle. Right? And that's the magnitude, v squared over r. To remember that, c is for centripetal acceleration, r omega squared. Right? V squared r or r omega squared. Okay, we are going to use this idea. If it's a cyclic quadrilateral, these two angles add up is 180 degrees, or these two add up 180 degrees, and that angle equals to this angle. Okay, the other thing that we are going to use is the same thing. This is 90 degrees. This is also 90 degrees. So we will produce the vector, produce a vector forward, backward there. This becomes a quadrilateral, right? CADB is a cyclic quadrilateral. So it means that if this angle is theta, this angle is also theta. These are ideas we are going to use in our derivation. Okay, so at time, we are going to derive the formula. So a particle move in a circle with speed v. So that's the initial velocity at time equals to 0. Suppose it moves to a small angle. That's a small angle. Delta theta. In a small time, that's a small time, a short time period. Right? From here A to B, in a short period of time, the velocity is in the direction. The speed doesn't change, speed still the same. That is your delta S. That arc length there, more distant. So remember, this is a cyclic quadrilateral. This one, CADB. Right? So distant move, that's a distant move. Right? We use our S equals to R theta, or delta S equals to R delta theta. Then we can rewrite, take the R, take the R across there, times dy. And our change in velocity, remember, is a vector, delta V equals to V minus R. So if that's our V, that's our V, that's our V. Final, minus, so if it's plus U, is in this direction, plus U, right? That's your U. Minus U is in opposite direction, that's the angle delta theta, this angle, equals to this angle, angle delta theta. So minus U is just opposite. Remember, the speed doesn't change, only direction changes. So the resultant, that one, delta V is a vector quantity, is here. There's a delta V. Right? This delta theta, this is also delta theta. Vertically opposite angle. So we can think of this as a radius, right? Because this angle is small. This is a radius. This is your arc length. Right? Same idea. So it's your radius times angle. I get your delta V. Okay, then we replace that delta theta with delta S over R. And we get our V delta S over R. Right? Then we go to our definition. A is dV dr, or delta V delta R. Okay. Right? Replace this one. Right? Delta V into here. So we got V delta S, right, here by R. That is this one. Right? This delta V placed here. That delta T is just a delta T here. Okay, then we can simplify. Delta S over delta T is your V. Right? That's your V equals to delta S delta T. Replace that, we get our V squared over R. Okay, anything not clear?
Okay.
Okay, let's now make the angle smaller and smaller so that the time becomes smaller and smaller until it's 0. Right? The direction still haven't changed. This is the original angle. Right? We make this angle become smaller and smaller, or this angle becomes smaller and smaller until your B approaches A. Same. Right? The only one, this is doesn't change. Minus U doesn't change. Only this one change. This angle becomes smaller and smaller. Right? And then if we make this one become 0, then this one becomes vertical. Right? Vertical. That means it's along here, towards the center. Right? Delta T approaches 0. Delta theta approaches 0. This angle becomes smaller and smaller until 0. This angle also becomes smaller and smaller. That means B approaches A. And then this V approaches the initial velocity. Same as here. That one becomes smaller and smaller, the angle. And then this one becomes vertical. Right? That's how I get our direction for acceleration. It's perpendicular to velocity. Alternative formula, right? We need to know how to derive this formula. Right? That's how we derive this formula. And use that relationship, replace V with R omega. Right? So it's R square omega square. R and R cancel, we still got one R. So it's R omega square. Okay. Condition for circular motion. Yeah, what are the conditions for circular motion? Can remember? Can? Right? All this must be in your head. Speed is constant. Right? The force is constant. Sorry, the speed is constant. The force is constant in magnitude. That's important. The force is constant in magnitude. Force is always perpendicular to velocity. That's important. Speed is constant, or force is constant in magnitude, not direction. Right? And force is always perpendicular to velocity. Right? And the direction, if there's a velocity, right? If you are told that this is direction of omega, then you must draw that direction as velocity. And this is the direction of acceleration or force. Right? Centripetal acceleration or centripetal force. Right? Along the radius. Okay, centripetal force. Force causing the particle to move in uniform circular motion is called centripetal force. Right? As it is pointing towards the center of the circular path. Right? Center. Centripetal force is towards the center. Rather than call it resultant force, we give it a special name. We call it centripetal force. To imply that the force is always pointing towards the center of the circle. Yeah? Remember, it's a resultant force. We know the value from our calculation, from our physics theory. Right? So if it has a mass m and moving with a speed v, angular speed omega, right, should be angular velocity lah. In a circle of radius r, then the resultant force is Newton's second law. Right? That's the acceleration. Either formula, the direction of acceleration, that's the velocity. Right? There's a person swinging this string, this heavy object in a circular path, horizontal circle. Okay, so we are just using Newton's second law. This one, acceleration times mass, that's all. So I'll get our centripetal force, the equation. Right? So car cornering, remember, we know the value, but it must be provided as something. Just like an object cannot move in a circle around the horizontally. It has to have a string to pull it. Right? Car cornering, like this one, car cornering. There's a centripetal force. There's your circle. There's a centripetal force. Right? So there must be provided by what? Friction. The car will tend to go there. Friction will pull it in. So friction is the centripetal force. Cork moving in a horizontal circle. Right? This person, that's your cork. That's your string. This person is swinging in the horizontal circle. So the centripetal force is the tension in the string. Without the string pulling it, it cannot move in a circle. It can move horizontally and then it will move in a parabolic path, fall down to the earth. Right? So the tension in the string, pull it in into a circle. Planet moving around the sun. Right? Gravitational force of the sun is pulling on the planets. Right? Then you can think of this is a sun. This is a planet, that's all. Right? There's the speed or velocity, direction velocity. There's gravity, gravitational force or force of gravity. Same, right? This, if you can think of satellite, this is the Earth, the same thing. That's the gravitational force. This is the centripetal force also. Motion in vertical circle with constant speed. Right? A bob of mass m move with constant speed v in a vertical circle of radius r and center c. Right? That's your vertical circle. Your center is c. That's your radius of the circle. You start at the bottom there. That's the mass. Right? That's the bob. That's your string. So at the bottom, that's your velocity, v. Speed also v. Force acting on the bob equals, right? We are going to calculate the forces acting on the bob. The weight will be coming down. Right? It's a vertical circle, so the weight will be pulling it down towards the earth. Tension, right? So that's your weight. Tension will be pulling it up. Right? The string will be pulling it up. That's your tension. So there are two forces acting. One is downwards, one is upwards there. Right? And then we know the resultant is towards the center here. That's your centripetal force. The resultant force is T minus your mg. Right? Resultant force is towards C. And we know that is equals your centripetal force. Right? That's the resultant force. We can calculate it from the speed and the mass and the radius of the circle. So replace that resultant force with mv squared over r. And we can find the tension. Right? We take this one across there. You can see that this is the largest. Right? In all the places there, the tension is largest here at the bottom. So it's also at this point, if the string is not strong enough, it will break. Then it will fire off as a tangent. And then it's just like an object thrown horizontally. Okay, so if we move up to the top there, what are the forces acting? Same thing. Look at the forces acting. The weight is still towards the downwards, towards the ground. And tension is also pulling it down. Right? Tension is the string is always pulling towards the center. So add the two together is the resultant force, T plus mg. Then remember that resultant force is given by this formula. Right? Not MA, because we can calculate the velocity. We can calculate the acceleration velocity and the radius. And then replace that resultant force here with mv squared over r. So we can find the tension. Right? Take this across there, becomes minus. So the minimum will be here. Minimum tension will be here at the top there. Tension is minimum. Any queries so far?
No, John. Just scared for next week.
Okay, so this one summarizes for you what we have just done. Right? At position A, the resultant force is upwards. At position C, the resultant force is downwards. Right? These are the equations. Don't memorize, just know how to derive it. If you look at energy, it's unlikely that the speed is constant. Right? It must have a greater speed here compared to the speed here. So you should be able to say, okay, at B, if that is the ground, this is near the ground, then the kinetic energy is half mvb squared. Then at A, the total energy is the kinetic plus potential. So kinetic energy is half ma squared plus your mgh, right? That height. So that height is just 2r. H equals to 2r. Okay, try this one. See whether you can get the answer. You can get the answer means you're right. A rubber ball with mass m. The mass is attached to a string 1 meter in length. What is the tension in the string if the ball moves in a horizontal circle? Frictionless stable. Frictionless stable with constant speed 4.2 meter per second. Just using the formula to calculate. Can get the answer. That's the formula to use. And put your value into the formula, that's all. Right? Tension provides the centripetal force. Right? Remember to change to SI unit. Right? You are told that's a string of 1 meter length. That's the radius. Right? Change the mass to kilogram. Mass to kilogram. That's the speed. Where that? Where 1 meter. Can 0.88 Newton. That's your centripetal force. Okay, let's carry on. Okay, have a go at this one. Right? It's tilting. That's your lift. That's your weight. That's your the wings. Then angle of theta with horizontal. So what provides the centripetal force? Any idea? What provides the centripetal force? It must tilt its wing. If not, it cannot move. It will drop down. Right? It can only tilt its wings if you want to move in a horizontal circle. So what provides the centripetal force? This one? There's a horizontal radius, horizontally. So this is the one. A component of this one will balance the weight and provide the centripetal force, right? That lift. Okay. Okay, so we can replace that lift. L is the lift, right? Provided by the aircraft because of the wings. So we can replace the lift with L cos theta that way. And yeah, W is still there. And then L sin theta. Right? Instead of L, we replace with these two values. So that one balance the weight. That's why the height will be constant. This is the one that provides the centripetal force. Right? So the horizontal component of the lift, L sin theta, provides the centripetal force. Okay, and then we are supposed to derive the equation. Right? Next one, we are supposed to show that banking means like that. That's called banking, tilting the wings. At an angle theta is given by the relationship, this one, where V is the tangential speed, right? It's moving out. Remember, this is moving outward towards us. R is the radius of the horizontal circle, G is the acceleration of free fall. Right? You're supposed to derive this equation. Okay, so we just use our the centripetal force. This is the centripetal force. Right? That's a centripetal force. Then for vertical equilibrium, this one is balanced by that one there. Okay, so that equation is this equation. So we just divide 2 divided by 1. 2 divided by 1. L and L cancel. Sin theta over cos theta is tangent theta. M and N cancel. So it's V squared over R. And then the G is at the bottom. Okay. Then they are asked to find the angle. To put in the value, that's all. 22 degrees. Okay. Right? You won't bother about the last part there. Last part you can. Application is just using this one. Okay. This is called banking. Right? Normally, it's the friction that provides the centripetal force. So it can be very dangerous if you have a flat road and you're moving in a corner, right? Especially on a rainy road, on a rainy day, the car can move into a bigger circle or what we call skidding. So it can be dangerous. So when we bang it, then usually friction is still there, but we don't depend on friction anymore. We depend on, right? That's your normal reaction. So normal reaction, we can replace it with your vertical force that balance this weight. That's your weight. And then there's a horizontal component. So that horizontal component of normal reaction provide the centripetal force. Right? So our safety depends on this one, not on friction. Of course, friction is still there. You cannot remove it. It's still there, but usually analysis, you will just neglect friction. Right? Banking, the corner for safety in cornering, horizontal component of normal reaction, this is one. Right? That's one that provides a centripetal force. Right? So if we look at this is horizontal curve, that's the road. The object is coming out towards us or going in, doesn't matter. If there's angle theta, this angle theta, same thing. There's normal to the surface. Okay, so that's the normal reaction. You must know that. And then, since we want horizontal circle, we resolve this normal reaction into horizontal component. Right? This is still the way. This and sine theta. Right? This angle theta. This angle is also theta. Right? It's all this you must remember. Right? So these two balance each other up for no vertical motion or for vertical equilibrium. For horizontal circular motion, centripetal force is provided by this component. That's what we are doing. Then we can take 2 divided by 1. Same as previously, 2 divided by 1. 2 divided by 1, M and N will cancel. We get V squared over R, V squared over R. Then there's a divide by G. That's what we get. Okay with that so far? Any comment? Yeah, any question? If not, we carry on.
Yeah.
Go
Yeah,
ahead
1
and-
hour finish already, lah.
Haven't yet, haven't yet. We started a bit late. Okay, so these are things you need to remember. Right? All these formula you need to remember. Know direction of centripetal force, tangential velocity, mass. If they are given, you'll be able to draw that. There's the angular displacement. If there's your angular velocity, there's your angular displacement. Not angle, angular displacement, angular velocity. Right? This is called tangential linear speed, linear velocity, or tangential speed, tangential velocity. And that's our definition for angular velocity. 2 pi over t, v equals to r omega. All this formula you need to remember. This is centripetal force. Acceleration is the resultant force. Okay, know how to use all this equation, memorize all this, and then condition for centripetal, condition for the object to move in a circle, or force is always constant in magnitude, and is always perpendicular to velocity. That's the two conditions. Okay, what's the answer for this one? I think we don't have much time, so let's go to past year paper. Okay, you can expect 1 or 2 questions to come out. Right? 11 topics, at least 1 question will come out, or 2, sometimes 2. Okay, what's the answer for this one? A particle of mass 0.02 kilogram is attached to elastic string, which is fixed at one end on a smooth horizontal table. The length of the string is 0.5 meter with a constant force 40 Newton meter minus 1 force constant. And the particle is moving in a horizontal circle of radius 0.6 meter. What is the angular velocity of the particle? Right? You won't have a question that's purely circular motion. Usually examiner will try to include 2 topics together so that we can cover 2 topics. So this cover your topic 8, Young's modulus and circular motion. Okay, what's the answer? Okay, what's the answer?
A.
What did I see? Right? Remember, at least you treat the string like a spring. So yeah, elastic force is kx. So this is the original length. This stretch length. Right? That's your force constant k. So you can calculate the force. Right? The centripetal force F. Right? That's your k. Original length minus your stretch length minus original length. Get your centripetal force. So elastic force provides a centripetal force mr omega square. You want to find omega, right? Take mr to the other side and then square root it and put in your value. That's the force. The force. Your mass. That's your mass. Right? The radius. Right? When you move in a circle, the radius, there's a force, that's why it becomes longer. Okay, good. A. Right? Next one, as I say, you need to remember this angle. It solve faster. Right? If you replace the weight with, right? This angle is theta, then W cos theta. Right? The weight can be replaced with that. Or for this one, we can replace normal force. Must be flexible to know all that. That angle is theta. Right? The angle is also theta, vertical opposite. So we can replace that normal reaction with our vertical force n cos theta and n sin theta. Okay, how about the answer for this one? A car of mass m is moving along a side slope, center O. So that's your center O, horizontal circle, as shown in diagram below. If n is the normal reaction on the car, that's the normal reaction. F is the frictional force on the tire. The centripetal force the car is
Donkey.
okay. Let's see. Right? Remember, we are interested in horizontal circle. I just shift the axis to here, easier to see. Right? So that's your vertical axis. Y, that's your X. So that's your angle theta. Angle theta, this vertical angle theta. So now the weight is still the same direction. Now I replace N, right? The N there with your N sine theta and N cos theta upwards there. Then your F, remember this angle is theta. This angle is theta, this angle is also theta. So F, resolve it this way. So it's F cos theta. So these two are the one that provide the centripetal force. Right? The centripetal force. The answer is C. Okay.
Okay.
A car is traveling on a bank road at an angle of 20 degrees to the horizontal. If the horizontal radius of the road is, right, that's the radius, 50 meter, and the frictional force is negligible, what's the speed of the car so that it does not skid? Right? It doesn't move upwards there, just stay horizontally. So what's the answer? It's better to derive the formula. It doesn't take a long time. If you want, you can memorize the formula that I derived for you. Yep. Right? Horizontal circle, remember? Right? So to resolve it into vertical, right? That's 20 degrees. This is 20 degrees. That's your replace the normal reaction with the horizontal component. That's your N sine 20, N cos 20. Right? That's your centripetal force formula. So if you resolve it vertically, that one, balance this one. That one provide a centripetal force. One. And you 2 divided by 1. As I say, you can remember the formula so much better. If not, just derive it. It doesn't take a long time. NV square over R. That one divided by mg, m and n cancel out. You want velocity, so take the R across there, R and then G across there, and put in your value. Answer is A. Okay? Okay, let's try one last one. Then we take 5 minutes break. An object at rest on a disk which rotate at constant speed. Which statement is true about the object? These are all partial questions. You can refer to your book there. Object rests on a circular disk which rotate with constant speed. Which statement is true about the object? I think we have done that already just now. Yeah, why take so long? Right? Linear momentum cannot be constant because it has a direction. Direction changes. Right? So false. Weight of the object provides a centripetal force. No. Horizontal circle, the weight is downwards. So incorrect. Magnitude of centripetal force, right? We are interested. Magnitude of centripetal force constant, correct? Because the speed is constant. True. Angular and linear velocity are constant. Right? Velocity has a direction. So it's not constant. Linear velocity is not constant. Angular velocity is constant, yes. Right? Because they're always going in one direction only. Answer is C. Okay, about this question. A remote control car moves in a vertical circle at constant speed, which is true about the linear and angular velocity of the toy car.
A.
Linear velocity changes direction, correct? Angular velocity is constant.
Yes.
You are right.
Because you were telling what's a linear velocity, they always change because it's different direction.
Okay, I think we will have to keep. If got time, we'll come back and discuss this one. If not, we'll take 5 minutes break.
Oh, very rare they ask this lah. So,
Not every year lah. Only this one. This one looks every year, but at least either B or C. We're not sure. Not sure. Okay, take 5 minutes break.
okay.